This is a video on Green's theorem. The question states, evaluate the line integral over c of x dx plus 2x minus y dy, where c is the boundary of the region lying between the graphs of x squared plus y squared equals 1 and x squared plus y squared equals 4. So we can sketch the curve C, and we get these two circles. And I'm going to assume that they meant that the outside circle is oriented counterclockwise, and the inside circle is oriented clockwise. The outside circle is of radius 2, and the inside circle is of radius 1. Now we'd like to use Green's theorem, but we can't right away, because if we look at our region R, it's not a simple closed region because it has a hole in it, or the curve is not simple either because it has two pieces. So instead we apply a little trick, and that is to add two extra curves along the x-axis in the region, like so. And we can think now of having two separate closed curves. One curve lies above the x-axis, and notice it's oriented counterclockwise, and the other curve lies below the x-axis, and you'll notice it's also oriented counterclockwise. Now we've added these extra pieces, but you'll notice that one piece goes to the right, and the other piece is the same piece but goes to the left. And when you take a line integral, going to the left and going to the right, they end up with opposite signs. So the line integrals cancel out, so we haven't really added anything. And the same thing for the other side on the negative x-axis. So now we can apply Green's theorem because we have a simple closed curve and then another simple closed curve. So I can calculate n sub x minus m sub y. N sub x is 2, and m sub y is 0. So I get 2 minus 0, and that's just 2. So next, I can apply Green's theorem and say that the line integral over the curve C is equal to the line integral over the curve C1 plus the line integral over the curve C2. And Green's theorem says that each of those are equal to double integrals over the regions R1 and R2 of n sub x minus m sub y. So we get the double integral over R1 of 2 dA plus the double integral over R2 of 2 dA. So I can factor out a 2, and then I can say that the double integral over R1 of dA, that's the area of R1. And the double integral over R2 of dA, that's the area of R2. So we get that 2 times the area of R1 plus 2 times the area of R2. And that's just twice the area of this total region. And the total region is this annulus, or this ring, and you can find that by taking the area of the outer circle and subtracting the area of the inner circle. We still have the 2, and that's pi r squared. For the outer circle, r is 2, so that's pi times 2 squared, minus pi times 1 squared, because the inner circle has radius 1. And that's equal to 4 pi minus pi, which is 3 pi times 2. And we can conclude that the line integral over C is equal to 6 pi. And I'm done with the problem.